We've looked at applying transformations to shapes, and today we're going to look at the opposite. What if we're given a transformation? How do we describe it? So, to start with, I want you to try and name the four transformations that we've covered, and also what information is needed to be able to apply each of them. So, pause the video, give this a go, write down the four, and then write down the information to apply each one. All right, not sure what order you would have done them in, but here's the first one. So translation, that was the first one that we studied. And to be able um, to know how to translate or move it, but translation is the technical word, we need to have this a vector. So it could be something like 3, 2. That means you go along in the x direction 3 and then up 2. And we also looked at ones with negatives in. So something like, I don't know, -2, -1. That'll be I'm going left 2 and then down 1. So just be aware of the positive and negative. It's a bit, so the first one's always to do with x, the second one's to do with y. It's a bit like a coordinate in that respect. The first thing is x, but it's not a coordinate now, it's a movement, and it actually exists. It's called a vector and it exists in its own right. It's sort of an arrow. It's got a direction and it's got a magnitude, a size. So once you know your vector, you can describe your translation. Second one, let's go over here. Rotation. So when we've got this, we might have some kind of, maybe a triangle, and then we rotate it around some sort of center of rotation in a certain way. So here I'm going clockwise. I could go the other way if I wanted to. And I need an angle, and at GCC it'll be 90 degrees or 180 degrees. In theory, 270, but that's the same as going 90, but the other way round. In theory, you could do other angles as well. And where you have the center of rotation is really important. It's basically where the shape orbits. So if it orbits around itself, it's just going to turn around itself, a bit like the Earth rotates on its axis. If it's away, it's like it's orbiting the sun or something like that. Okay. Oh yeah, and also, so finally, so if the angle is 180 degrees, then you don't actually need a direction because you get clockwise and anti-clockwise would go the same way. Right, third one. So there's three bits for that one. Third one, reflection. We're back to just having one piece of information. We just need to know a mirror line. So you've got some sort of shape. You put a mirror line in. Here it's a vertical mirror line. It'd be something like x equals 3. And then you go that distance to the mirror line and you go the same distance. And you get this reflection going on through the mirror line. You can have y equals mirror lines, so this would be a horizontal one, and there's two special cases. As y equals x, don't forget that is the diagonal line that goes to the origin, and there's also y equals minus x. Those are the ones that are sort of typically seen at GCSE. In theory, you could have other lines as well. That would make it more complicated, but the same process would work. And the last one, enlargements. So here you need a scale factor. That's going to tell you how much bigger or smaller your shape gets. For one, it's going to stay the same. But we've also looked at negative enlargements. That's when instead of going out through, well, actually, for that to make sense, you need to talk about your center of enlargement as well. So if I've got a shape, if I go out through with ray lines, I can make it maybe twice as big. Over here, this would be a scale factor 2. Scale factor 3, even bigger. And then we talked about what if you get negatives, you actually start from the shape and you go through the center of enlargement and it's going to end up the other side. And if you got, say, a triangle, it will end up flipping round. So we spent a bit of time on that. You've got a center of enlargement, really important. You kind of use that with ray lines or like that kind of idea anyway. And then you've got a scale factor with these negatives coming in as well. So hopefully you're happy with that. You're happy applying all four of those transformations. Let's move on and try to describe some that have already taken place. Right, I've got some grids and we are trying to describe the transformation that's going on. So in the back of your mind, you've got these four transformations and you've got to decide which it is. And I think if I was doing it, I would think, right, is it a translation? Does it look exactly the same at the end? And then if it doesn't, is it obviously a rotation? Like, has it kind of, can you see that it's like moved around a point? If not, is it actually probably in between that? You're thinking, is it an enlargement? Is it got bigger or smaller? And then maybe rotation and reflection, the ones at the end. But that's kind of the order that I'd be thinking about it in. So this one, I can see that it's exactly the same orientation, so it's going to be a translation. So I'm immediately just going to write that down. Translation, or you could say translates. And then we just need the vector. So if I just pick a point, maybe this top point, I'm doing A onto B. Okay, I go along 2, 3, 4, 5. So the top bit of my vector is going to be 5, and then I'm going up 4. So translation by 5, 4. And we see if we pick a different point, maybe this bottom right hand corner, 1, 2, 3, 4, 5, 1, 2, 3, 4. It's going to work for that one. So, I can check with a second point. I think that's worth doing. But I see in both cases I get 5, 4. And the same would be true for the bottom left corner. All right. What about this next one? Well, again, it's exactly the same kind of thing. It's not changed orientation. So again, it's going to be a translation. And in fact, it is the same two shapes. It's just this time I'm starting from the right hand shape. So now I'm going to go 1, 2, 3, 4, 5, but that's to the left. So it's going to be -5. And then I'm going to go down 4. So I put this in purposefully just to show you, that's basically the opposite. You just stick a negative in front of it. These are opposite operations, translating A to B and then B to A would give you this. And if you added those two vectors together, something that we will do at some point, you would actually get 0, 0. So 5, you'd add the tops, 5 minus 5 is 0. You'd add the bottoms, 4, I'd say 4 plus -4, which is the same as 4 minus 4, which is 0. And you wouldn't move anywhere. That makes sense, doesn't it? If you translate and then you translate back, it's equivalent to having not moved anywhere. Next one, so I can see this is not an enlargement, it's the same size. It's not a rotation, it's going to be a reflection. So we just need to get the mirror line in. Remember, that was the one piece of information. So what a good idea, I think, is to just connect some corresponding points. And then I know that the mirror line is exactly halfway between those two corresponding points. So it's going to, like, part of the mirror line is going to be there. And if I do it for this bottom left point, it's going to be there, and that's going to be enough. I can then draw my mirror line. By the way, do feel free to pause the video and just have a go at these questions yourself. I'm just going through them. So this is a reflection. We need that keyword in there, in, and this is going to be x equals -1. So that has to be there. We're not using, a line CD or anything like that. We need the equation of the line. That's enough. That's what we need. All right, let's look at the next one. It's not a translation. It hasn't just moved. It's not getting bigger. It's not a rotation. Right, so what is it? It must be another reflection. It's a bit harder to see, but let's just kind of go with it. Let's connect corresponding points. And that would be where the mirror line goes through. And if I do it over here as well, like diagonally, then 1, 2, 3, 4, 5. So it's going to be there, halfway in between. Probably worth doing it for this one as well. So this is 4, so it's going to be there. So the mirror line is going to go through those points. And if I draw it in, we've got this diagonal line going that way. So it's another reflection. It's in y equals -x. Everywhere along that line, you can see when x is -4, y is 4. When x is 3, y is -3. They're the same numbers, just I've taken the negative. That is a line that you're expected to basically recognize very quickly. The same goes for y equals x, which is this one here. But I'll get rid of that. But that's another classic diagonal line that you could be expected to recognize or draw. Let's move on. This next question, we start from A, we're trying to get to B. It's not a translation, it's not an enlargement, it's not a obvious reflection, and yeah, it's not actually a reflection. It's going to be a rotation. You can kind of see that if you rotate it around itself, like it would look like that. We just got to find the center of rotation, but we can get some key information down to start with. It's going to be a rotation. And we can either think of it going this way or the other way, but it makes sense to go the shortest angle. So it's going to be rotation by 90 degrees anti-clockwise. Because you can see I've got a little arrow. If I put this little arrow on there, if it moves around, it's then going to be facing the left, and there's going to be a 90-degree angle between that. Right, we just need to get the center of rotation. And there's kind of three levels of complexity for trying to get this. And the more advanced, the more precise and mathematical, I suppose, but also the more difficult. So the first way is actually, if I was you, I'd get some tracing paper, I'd sketch the shape, and then I'd just try the origin, see if it works. And if you do that in this particular case, then you will find that it does. This is me rotating it around the origin, it will perfectly fit on. So the answer is anti-clockwise about 0, 0. What if the origin doesn't work though? Well, okay, second level of complexity really is that when you rotate a point, let me draw a circle. So when I rotate this point, if I take 0, 0 to be the center and I put my pen on it and rotate A around it, if I take the point at the top, then actually as I rotate it, it does move around this circle here. And we can use that to help us find the center of rotation. So imagine you don't know where the center of rotation is. You can't draw the circle, but you can kind of imagine what's going on. And the key point is that the corresponding points, this one and this one, they're going to be the same distance away from the center of rotation because it's the center of the circle. So it's the center of rotation couldn't be over here, for example, because this point is much closer to that one there than to this one here. So you can basically rule it out, and you're left with just a few points maybe to try. And it's going to be it's not going to be like here. It's going to be on the where these lines intersect. So if you just try a few, then well, we'll see in the second example a bit more. But yeah, if you tried like around here, here, and here, then you would and you put your tracing paper down. You've drawn your shape, and then you just put your pencil in different places. Then you'll see actually yes, it's this one here in this particular case that makes it line up. So that's the second level of complexity. And to be honest, I think that is the one that is probably the quickest at GCSE. The third level of complexity I'm actually going to talk about right at the end of this video because it gets quite technical, and sometimes I get asked, is there not a way of doing it that will guarantee me the center of rotation? Well, the answer is yes, there is, but it's probably quicker to just do this method that I just explained rather than do the third method that I'm going to explain a bit later on. Okay, so I'm gonna leave the third method, but we'll come back to it. So this one here, A to B, right? We can rule out all of them again except rotation. Oh, by the way, yeah. So you could have said 270 degrees clockwise. If you're going from B to A, it would just be reversed. It would be rotation by 90 degrees clockwise. So just be aware of again the inverses that exist. Right, this one here is going to be a rotation by, and you can see if I've got my triangle kind of pointing up, and here it's pointing down. So this is going to be 180 degrees. In this particular case, I don't need to specify a direction because it doesn't matter if I do it anti-clockwise or clockwise. However, we do need to get the center of rotation. And this time the origin doesn't work. So if you tried that, you would have seen, if you got some tracing paper, drew over A, rotated about 0, 0, it doesn't work. So we need maybe method 2, and that is to think about the points rotating around the circle. I can see that the origin is not going to work because look, it's only 2 away from that top point, but it's 2 and 4 along. You could work out the length of that using Pythagoras theorem. So away from that top point of A. So I'm going to need to move it closer to A. So if I maybe tried it here, And obviously you could try this with your tracing paper, but again, it's not going to work because look, it's that away from the top bit, but it's all that away from that top bit. So it's got to be exactly the same distance. And if I go for here, then suddenly I see that it does work. It's 2 along and 2 up, and it's 2 along and 2 up. And if I checked with another point, I'd see, look, it's that distance away and it's that distance away. This is going to be the center of rotation. You don't have to think about it in that level of detail, actually, but that, you know, hopefully it makes sense what's going on. And if you rotate it around this point, 0, 2, okay, because you should always do that with your tracing paper, then it lines up exactly. I should have said, like, if it doesn't line up exactly, then it means, you know, if you ended up over here, then again, you'd know that the center of rotation is not correct. So using this method, we're not just randomly guessing, we're not just like trying it over here because we know that can't work. We're kind of highlighting an area where it possibly could be and maybe trying some around that. That's a good enough level to be able to work out the center of rotation. So in this case, it's going to be about 0, 2. Okay, nice one. Finally, here we are, we're at enlargements. And actually, I don't think these are that difficult. You know, I think doing the enlargements when you first do them is quite tricky, but actually describing them is not quite so bad if you remember the main principle, and that is that we are projecting from a point. Then it goes, basically, it uses ray lines that go through each single point. So if you just use that principle and you connect your corresponding points up, you've got to do it a bit carefully. So I can see I'm going along 1, up 3. I'm going to go 1 long up 3 again. Okay, don't try. It's very easy to get it slightly out, but I don't want to do that. So, okay, that looks pretty good for that first ray line, and I'm just gonna draw more. So if I use the bottom left-hand corner, okay, it's along 3, up 3. So just keep going the same gradient to make sure the line. And you can already see that they've met right there. That will be the center of enlargement. If I do it for this top point as well, probably the easiest one, maybe the one I should have started with, then there we are. We've got this single point that gives us the center of enlargement. And so what I need to write down is enlargement by factor. And then how much bigger has it got? Well, it's 2 here and it's 4 here, so it's factor 2. I think sometimes we say scale factor, but I'm just going to say factor 2 here. About 4, 4. That's it, not too bad. Try the next one yourself. So this next one is going to be exactly the same. Actually, I've done this on purpose. I've made the center of enlargement the same, but this time I'm going from the bigger shape to the smaller shape. I'm just reminding you about what happens when it gets smaller. So this is the inverse operation essentially to get back to the original shape. If I started here, made it bigger, how would I get back to the original shape? It'd be an enlargement by factor 1/2 this time because I'm going from 4 to 2. But it's still about the same center of enlargement. So for these inverses, you'll just end up the same center of enlargement, but you'll take the reciprocal, essentially, of the scale factor. Okay, nice. Hopefully happy with that. This ray line argument is really, like, even though I don't always say to use it when you're performing the enlargement, it is absolutely essential when you are describing the enlargement to get the center of enlargement. Okay, finally, what about this one? So it's again, it's got to be an enlargement, doesn't it? Because it's got bigger, so you can immediately like figure that out. It's just that now it's upside down. So what is going on? Well, let's get our ray lines in. We just got to think carefully about the corresponding points. Those two are going to be corresponding. These two. A bit harder to do this like go by counting along. I suppose, but this is good enough. And I can see again, they all meet at a single point, and this is going to be my center of enlargement. But this time, right, I'm going from the shape through the center of enlargement to the other side. This is a negative scale factor. So it was 2, it's now 4 in length, but it's flipped around, so it's going to be factor -2. About 1, 2. Okay, I like it. Just be, recognize that it's flipped, and then just do the same as before, essentially. Okay, this last one, very similar. Just wanted to put another one at this, because I suppose this is getting a bit complicated. Let's do the same again. Corresponding points, just join them up as accurately as you can. Okay, we can already see it meeting there. Let's check that this one meets there. Yep, it does. So that is going to be my center of enlargement. And this time, okay, the best thing to do probably is look at the heights. 1, 2, 3, 4, 5, 6, 7, 8, and then it becomes 4. So it's going to be factor -0.5. Again, it's flipping round. I've gone from the shape through the center of enlargement, and it's going to be about 3, 2. Now we have it. Quite a few examples, but hopefully you've tried them yourselves. I've just got to wait one more point, and that is to say that this one up here, when I was doing my rotation, I did talk about this when I did enlargements. Actually, technically, this could also be described as an enlargement. If I draw my ray lines going through it, then I see that they all meet up about that point 0, 2. So an alternative to this rotation by 180 degrees would actually be an enlargement by factor -1 about 0, 2. So they are the same thing. When you do a rotation by 180 degrees about a point, it is equivalent to doing an enlargement by factor -1 about the same point. And that actually is quite a nice, if you recognize that it's a rotation of 180 degrees, it's not, you can actually just draw the points. You can just connect the ray lines, and then you can either say it's a rotation about the point or an enlargement. It won't work. It won't always work for other ones, like if it's not 180 degrees. So you have to resort to my other methods for working out the center of enlargement. But if it's 180 degrees, this will work. It's quite a nice thing to know, and it's nice to see the relationship between enlargements of factor -1 and rotations again. Over to you then. Here's grid 1, a load of questions. Use the grid below to describe the transformations listed. So A to B, A to C, and so on. See if you can do it. You've got to write it in full. You've got to write the transformation name and then all the other information needed. I'm going to show you the answer so you can check. So that is what you should have got. I think A to C, you could have said that it was an enlargement by scale factor -1. Just be aware of that. We talked about that. Okay, the same for E to G. Here's a second one, bit more going on. Okay, can you do the following descriptions? Hopefully you've got a worksheet of this that you can write on. Like, it's very hard to do this without actually using a worksheet, but I'm posting one up. Okay, here's the answers. So we've got all sorts this time, reflection and y equals -x. Hopefully you are happy with that. So well done on your effort. Finally, because that sheet didn't have many negative enlargements, I've got a whole dedicated one on that. So pause the video, give these a go. Can you describe the transformations from A to B? Go for it. Right, here are the answers. So each one should say, and this is abbreviated, it should say enlargement by scale factor such and such about the center such and such. It's just abbreviated answers to make it a bit quicker. So if you're happy with that, then you've hopefully mastered describing all your 4 transformations and you're ready to look at combining transformations, basically the final bit of this topic. Here is a bonus video then on method 3 of working out the center of rotation. I said try the origin. I said if not, if you want to be a bit more mathematical than that, then realize that actually when you rotate something, it's essentially moving around a circle, and so the center of rotation is going to be the same distance. It's going to be the center of the circle, and it's going to be the same distance away from corresponding points. So that can help you find it. If you want to be as most precise as possible, then here's how you can do it. So first things to know is there's a circle theorem that you need to be aware of to understand this method, and it's as follows. If you draw a chord, that is just a line going from part of the circle across to another part of the circle, then if you then draw a perpendicular bisector, a line that splits it into 2 and is at 90 degrees, it will necessarily go through the center of the circle. So I'm gonna demonstrate that, I think. So I did do it with a line. I was going to show you what a perpendicular bisector was, but I'm going to do it with the circle there as well. So we've got everything going on. So if I just draw a random chord, I'll do it over here. Right, now this next bit kind of requires you to remember what a perpendicular bisector is, and you might not. Sorry, my compass is all the way up here. So let's go through that. You will encounter this at some point in GCSE if you've not already. It's also covered earlier on in Key Stage 3 and the like. Right, for this, I want to draw the perpendicular bisector of my chord. So I just treat it as a straight line, essentially. And I put my compass there, and then I draw some arcs going round, like so. And then I move it to the other point and do the same thing. Probably, oh no, I can't. Okay, you're meant to go beyond halfway. I could have maybe gone a bit more beyond halfway, but I do get these little arcs coming in. It is good enough, and I can draw my line that goes through it. And what the circle theorem says is that essentially, this will go through the center of the circle. Now I don't know where that is at the moment, so actually, if I wanted to, I could draw another chord and do the same again. I could find the perpendicular bisector of that. So this time I'm going to make sure I go beyond half, like a fair bit beyond halfway. Okay, I'm drawing my perpendicular bisector again, so I draw this arc. I told you this is a technical method, but it will work out in a minute for rotations. Okay, so if I do that and draw a line that goes through it, then where they meet, so because they both go through the center of the circle, it must be that this is the center of the circle. And yeah, quite a nice little application in its own right. How's that going to help us with this transformation? Because I said before that when you rotate around a point, you're basically moving it in a circle. So you wouldn't have this in the question, but this is what's happening. And so if you connect your corresponding points, like here and here, then you've created a chord for this red circle. And then if you draw the perpendicular bisector, it will go through the center. If you do the same for the green circle, so these 2 points, for example, if you draw the perpendicular bisector of that, it will also go through the center. And then you can work out the center of the circle and hence you've got the center of rotation. So I'm going to do it without the circles in there, but I just wanted to illustrate what is actually going on. All right, I'm going to draw this red line. These I got to work out that these are my corresponding points. I'm then going to draw my perpendicular bisector. Now I'm actually going to I'm going to cheat a little bit, like, because I can also, like, if you're watching this video, you probably have done stuff on. No, you might not have. Okay, I'm not gonna. I'll talk about it in a minute. How you can draw the perpendicular bisector really quickly. But let's do it the way I just showed a minute ago. Okay, just go a bit beyond halfway. Do the same the other side. Then draw this a line going through these 2 points. So I know the center of the circle, center of rotation is somewhere along this line. I don't know where. If I do the same for another 2 corresponding points, let's say these 2, I do the same again. And this is why I wouldn't necessarily recommend this method, because it's taken longer than if I just maybe guessed it, but it is more precise. Okay, I'm now drawing the perpendicular bisector of this green line, gone beyond halfway. So I know that the center of the circle is through the perpendicular bisector, and there we have it. Look, we can see it's going to be, I don't need to do it for the third one, it's going to be here. So it's going to be a rotation by 90 degrees clockwise about that point there to 0. Sorry, I can't write the comma in because I've reached the end of the page. There we go. Okay, that is the third method how you can do it. What I was going to talk about before is that actually you can use knowledge of reciprocal lines if you wanted to draw the perpendicular bisectors. So this red one, for example, I can see the gradient is -2, and so the perpendicular bisector is going to go through this point that I'm hovering over with a gradient of a half, because 2 gradients must multiply to give -1. So I could have done it really quickly. I could have just gone like that. And I could have done the same for the green line. So I just wanted to mention that's quite a lot going on in this question. Sorry, in this video. But that is a summary of how you can work out the center of rotation using these, these more advanced methods.